In this episode, we will talk about parallel scaling law for language models. We've got some really groundbreaking research here. It's tackling a major hurdle in the world of large language models.
Hmm.
How do we make them even more capable without hitting these massive walls of computational cost, both when we're training them and, crucially, when we're actually using them?
Exactly.
Yeah.
Yeah, the work we're diving into today really grapples with the fundamental economics, you could say,
Yeah.
of scaling up these incredibly powerful AI systems.
Right.
For a long time, the main way to make a language model smarter was, well, just make it bigger. Add more and more parameters, those internal dials and knobs that let it learn.
Like DeepSeek V3, that thing's huge.
672 billion parameters,
Yeah.
just staggering.
Yeah.
The sheer size demands enormous compute, enormous memory. It makes it impractical for a lot of real-world uses.
Okay.
And the other main path has been increasing computation during inference.
Yeah.
Basically, making the model think harder for each question by generating longer chains of reasoning.
Right, like generating hundreds of steps.
Yeah, they mentioned needing like 900 reasoning tokens for relatively simple problems in some cases, which, adds significant time. It can be pretty inefficient.
Okay, let's unpack this a bit. So traditionally, it's either scale up the size parameters, which means huge space costs,
Mm-hmm.
or scale up the thinking time at inference, which means high time costs.
Yep.
And these limitations, the memory drain, the waiting time, that's really the core problem this new research is trying to fix, isn't it? They're asking, can we get better performance without these escalating costs?
Precisely. And the answer they propose is this really fascinating third way. They call it parallel scaling, or ParScale.
ParScale, okay, parallel suggests doing things at once. How does that work inside a language model?
So the core innovation with ParScale is boosting the model's parallel computation. And this happens during training and during inference.
Okay.
Instead of just one input, one output, ParScale applies multiple, distinct, and importantly, learnable transformations to the original input.
Learnable transformation. So you take the input question.
Yeah, imagine taking your original question and creating several slightly different versions of it. Each one may be nudged in a slightly different direction. They call the number of these parallel streams P.
Okay, I think I can picture that. So start with one prompt. Now we have P slightly different ones. What happens next?
These P-transformed inputs are then fed simultaneously in parallel to the exact same underlying language model.
Ah, okay. So we're not actually making the core model bigger in terms of parameters here.
Exactly, that's key. We're leveraging the existing intelligence, just making it process these different angles on the input at the same time.
Got it. So same neural network, processing P, different takes concurrently. How do you get back to a single answer then?
Right, that's the final piece. Dynamic aggregation of the outputs. The P different outputs from the parallel streams. They get combined into one single coherent final output. Using a smart learnable mechanism, it dynamically figures out how much weight or importance to give to each parallel output. It learns which of these slightly different lines of thought seem most useful for the final answer.
Wow, that sounds really elegant, almost like having a mini committee inside the model, each looking at the problem slightly differently.
Yeah.
And then a smart system combines their insights, weighting the best ones more heavily.
Exactly. And the big advantage, like you said, is reusing the model's existing knowledge. That should lead to way better memory efficiency compared to just brute force parameter scaling.
Makes sense. Scaling through parallel work, not just sheer size.
Precisely. ParScale scales by orchestrating the existing capacity to work in parallel on diverse takes of the input. And they stress this isn't just for one type of model or data set. It's meant to be broadly applicable.
Okay, interesting. Now, the paper mentions in inspiration something called Classifier Free Guidance, or CFG, from diffusion models. Image generation stuff. How does that connect? Seems a bit removed.
Yeah, it does seem a bit afield at first glance. But CFG, used in those image models, often involves doing two forward passes. One with the normal text prompt and another with the slightly perturbed version, maybe less specific.
Okay.
Then they combine these two results using some rules to often get a better, more prompt-adherent image.
So, like, ask it normally, ask it slightly differently, blend the results.
Pretty much, yeah. And the ParScale researchers thought, well, maybe the real benefit of CFG isn't just the specific blending rules, but the simple fact that you're doing the core computation twice.
Ah, the double computation itself might be key.
Exactly. So they asked, what if we scale that up, go beyond just two streams in language models, and crucially, make generating those parallel inputs and combining the outputs learnable parts of the model? That was the leap to ParScale.
Got it. So instead of just perturbing the input like CFG, ParScale uses these learnable input transformations. How does it learn those? You mentioned prefix tuning.
Yeah, prefix tuning, basically they stick, keep it short, learnable sequences of tokens, the prefixes, onto the start of the input.
Okay.
Think of each prefix as a kind of subtle, adjustable instruction or context nudge for each parallel stream. The model learns to tweak these prefixes during training to make the parallel processing more diverse and useful.
Right.
Technically, in the transformer architecture, this ends up meaning different key value caches for each stream, helping keep their contexts distinct.
Okay, that clarifies it. Different starting points, different initial context for each stream. And then combining the outputs, you said a dynamic weighted average using an MLP, a multi-layer perceptron. Why dynamic and learnable there?
Good question. By making the weighting dynamic with an MLP, the model learns which parallel path is giving better clues for predicting the next word. The MLP looks at all P outputs and assigns weights before summing them up. It adapts its strategy based on the input and how the parallel streams are doing.
Makes sense.
And interestingly, they found the specific way they did the code, the input transformation or output aggregation didn't matter that much. The big lever was really just P, the number of parallel computations.
Yeah. Okay, this is where it gets really fascinating. They developed a theory around this and proposed a new scaling law. We know the chinchilla law relates model size, parameters, to optimal training data. How does ParScale change that picture?
Right. They build directly on the chinchilla foundation. Lemma 3.1 in the paper basically states the chinchilla law. Loss, how wrong the model is related to the number of parameters, n.
The formula is loss equals like A over N to the power of alpha plus E, right? Where E is noise in language itself.
Exactly. A and alpha are constants, n is parameters, E is that irreducible language entropy. That's the baseline. Bigger n, lower loss, essentially.
So how does ParScale with P parallel streams modify this?
So their proposition 1 gives the theoretical parallel scaling law. The loss L with P streams and n parameters become, well, it's a bit more complex. It's roughly L equals A divided by n times P to the power of 1 alpha times this new term, diversity, all raised to the alpha plus E.
Ooh, okay. Diversity, that sounds key. What's that capturing?
The diversity term depends on rho. Rho is the correlation between the errors technically, the relative residuals made by the different parallel streams.
So rho measures how similarly the parallel streams mess up.
Pretty much, yeah. High rho means they make similar mistakes. Low rho means their mistakes are more independent, more diverse.
Okay. And how does diversity with rho inside it affect the loss?
Mathematically, diversity is related to P1 plus 1 raised to a power involving alpha. The key things they found are, 1, if rho is one perfect correlation, all streams make identical errors. The diversity term cancels out the P term's effect, and you just get the original chinchilla law back.
So if the streams aren't diverse, ParScale doesn't help theoretically.
Right. Though they note even the random initialization of prefixes usually prevents perfect correlation in practice.
Okay, makes sense. What's the second insight?
Second, when rho is not 1, which is the usual case, loss is inversely correlated with P. And ideally, if rho is 0 totally independent errors, loss scales roughly as P to the power of -1, which fits nicely with ensemble theory. More diverse predictors in an ensemble lead to better overall predictions. ParScale acts like a learned ensemble.
So theoretically, P parallel streams could give a similar loss reduction to scaling parameters by some factor related to P and this diversity. The paper suggests it's like scaling N by P1 alpha diversity. That's pretty big, getting similar gains without a bigger core model.
Exactly, a really powerful theoretical motivation, which led them straight into large-scale experiments to see if this holds up in practice and find a more concrete empirical law.
Right, the experiments. Pre-training transformers up to 4.7 billion parameters, up to P8 parallel streams on datasets like Stack V2 for code and the general pile dataset. And crucially, fixed training data, 42 billion tokens to isolate ParScale's effect. What did they find?
What they saw was this very clear, consistent logarithmic trend. Loss went down as P increased, but the gains got smaller with each doubling of P. So biggest jump from P1 to P2, then smaller gains going to 4, then to 8.
A logarithmic relationship.
Yeah, which led them to propose their practical, fitted, parallel scaling law. Equation 5 in the paper.
And what does that look like?
It's similar to chinchilla, but the denominator gets modified. Its loss, L equals A divided by n times k times natural log of P plus 1, all raised to alpha plus E.
So the n term is effectively boosted by k ln p plus 1. That ln p captures the logarithmic benefit.
Exactly. A, K, alpha, E are fitted constants. L is the natural log, base E.
And did this fitted law match their actual experimental results well?
Remarkably well. They reported R-squared values, the goodness of fit, up to 0.998. Super high fit for both data sets. Strong empirical backing for this logarithmic parallel scaling.
Yeah.
And interestingly, the K value, which kind of controls how much benefit you get from P, was higher for the coding dataset stack V2, around 0.39, than for the general pile dataset, around 0.33.
What does that suggest?
It suggests perhaps that parallel computation helps more for tasks needing complex reasoning, like coding, compared to tasks relying more on memorization, which might be more dominant in pile.
That's a really interesting thought. Maybe parameters are more about memorization, while computation, especially parallel computation, is more about reasoning.
That's the conjecture.
Yeah.
And figure 3, showing how loss curves flatten with more parameters, visually supports this, suggesting that for bigger models, boosting computation via ParScale might be increasingly the better way to improve.
And did this translate to better performance on actual tasks, not just lower training loss?
Absolutely. Tables 2 and 3 show downstream results, coding benchmarks like human eval plus MBPP plus PROMs and general tasks too. Consistent gains with increasing P across the board.
Any standout results?
Yeah, their 1.6 billion parameter model with P8 performed comparably to a much larger 4.4 billion parameter baseline model on the coding tasks.
Oh.
On general tasks, that same P8 1.6B model was more like a 2.8 billion baseline. Still good, but again, the boost seems particularly strong for reasoning-heavy coding.
Okay, now the crucial part. Inference cost. What's the price you pay for running these P streams when you actually use the model? They looked at memory and latency, right? Not just FLOPS.
Right. They argued FLOPS isn't the whole story, because memory access can be the real bottleneck. Figure 4 shows the results. For memory, ParScale adds very little overhead.
Really? Even with P streams?
Yeah, because the extra ParScale parameters, the prefixes, the aggregation network, are tiny compared to the main model. And while the KV cache grows with P, it's still usually much smaller than the model parameters themselves in terms of memory footprint. So much more memory efficient than just using a vastly larger model for the same performance.
That's a huge plus, especially for edge devices, phones, things like that. What about latency, the speed?
For latency, at small batch sizes like processing one query at a time, common for interactive use, ParScale adds minimal delay.
How come? Isn't it doing key times the work?
Sort of, but it shifts the bottleneck towards parallel computation, which GPUs are great at, rather than memory access. So for batch size 1, it's very efficient. As batch size increases, the parallel work does add up, making latency higher than the baseline P1 model.
But still better than just using a bigger model.
Yes, it remained more latency efficient than parameter scaling for equivalent performance, at least up to batch size 8 in their tests.
So for those low-resource, small-batch scenarios, ParScale looks like a win-win. Lower memory and lower latency increase compared to just scaling up parameters.
Exactly. The example they gave. 1.6B model, P8 ParScale versus parameter scaling for the same performance at batch size 1. ParScale had 22x less memory increase and 6x less latency increase. That's substantial.
Well, that really drives home the potential for practical deployment. Okay, but what about training cost? Doing P-forward passes sounds expensive during training.
It is potentially more costly. So they proposed a smart workaround, a 2-stage training strategy.
Ah, okay. How does that work?
Stage 1.
Yeah.
Standard pre-training of the base model on tons of data. They use 1 trillion tokens, get the basic language understanding down. Stage 2, apply ParScale training, but only on a much smaller data set that use just 20 billion tokens.
So build the foundation first, then teach it the parallel processing trick with less data.
Exactly. The idea is it already knows language. Stage 2 focuses on leveraging parallel computation for better reasoning.
And did that work? Did it still show the ParScale benefits?
It did. Figure 5 shows the loss curve. There's a small initial bump in loss when ParScale kicks in for P1 in Stage 2. The new parts are randomly initialized, but it adapts quickly and then shows those logarithmic gains predicted by the scaling law.
And downstream performance after 2-stage training.
Table 4 shows clear gains. A 1.8B model trained this way showed consistent improvement across general, math, and code tasks as P increased. They highlighted a big jump on math reasoning. GSM-8K benchmark saw a 34% relative improvement going from P1 to P8.
Wow. Again, reinforcing that reasoning benefit.
Definitely. And their P1 baseline from this 2-stage process was competitive with other similar-sized models, showing the base training was solid. They also showed ParScale helps even when applied just during instruction tuning later on.
Okay, one last thing. They even tried applying ParScale to an existing model, right? Qwen 2.53b.
Yeah, to show its versatility.
Yeah.
They did continued pre-training on Pile and Stack V2, Figure 6, A and B. Even on that already well-trained model, ParScale could still squeeze out improvements.
Impressive.
And, maybe even more practically, they tried parameter-efficient fine-tuning, PEE. They froze the original Quinn model and only trained the small added ParScale parameters. Figure 6c shows it still gave significant gains, especially in code generation.
That's huge. Take an existing model, add ParScale bits, train only those bits, and get a boost.
Exactly. Super practical. And because the main model is frozen, it opens up possibilities like dynamically changing P during inference. You could switch between, say, P1 for speed and P4 for higher quality without reloading different models.
Adaptable performance on the fly. Very cool.
Lots of flexibility there.
Okay, so let's try and summarize the key takeaways from this deep dive. ParScale looks like a really promising inference-efficient way to scale LLMs. It boosts parallel computation, reuses existing parameters smartly, leading to this parallel scaling law where P streams act somewhat like having logarithmically more parameters, but with much better inference efficiency, especially memory-wise and for low batch sizes.
Right. And the two-stage training makes it more practical to train. Plus, it can even be applied effectively to existing models using parameter-efficient tuning.
And a recurring theme seems to be its particular effectiveness at boosting reasoning capabilities.
Definitely seems that way. It provides strong evidence that just scaling computation, maybe even more than parameters sometimes, is crucial for unlocking deeper reasoning. And it's great they release the code and models too.
Absolutely. This has been really enlightening. It definitely challenges the bigger is always better parameter-centric view. Which leads to a final thought, maybe for you, the listener, to mull over. Given how ParScale highlights the power of computation itself, how might we need to rethink the path towards AGI, artificial general intelligence? Is the answer just ever bigger models, or is it about finding smarter architectures that balance parameters with massively parallel, maybe dynamically adaptable computation in entirely new ways?
That's a fascinating question. Really gets you thinking about the fundamental trade-offs and the future direction of AI architecture. A great place to leave it.